Good morning, everybody. We're going to go ahead and get started right away because we have to finish Chapter 7 today. And Chapter 7 is probably one of the toughest chapters, math-wise. Concept-wise, I think it's Chapter 4. Math-wise, I think it's Chapter 7. So, if math and you are like oil and water, definitely going to want to listen up and get started early on that Chapter 7 homework for mastering chemistry. Are there any questions about last time, logistics, where we're going with the class? This is a good time to ask them. Otherwise, we are going to go right forward into Chapter 7. So let me know if you got questions or if you're ready to start. Then let's roll. My OG crew, y'all always log in on time. I appreciate that. I know people have classes and stuff, but with this type of setup, we need every minute. So last time we kind of went through molar mass, but it was quick at the end of class. So I want to start here, and then we'll finish out the chapter. We talked about the concept of the mole and how that's related to Avogadro's number. And we can do calculations to figure out how many atoms are in 5.2 moles of iron or something like that. We're not going to necessarily review that specifically, but we will be going over it as we do calculations throughout the rest of this chapter. But that's kind of the relevant stuff for what we need going forward for Chapter 7. For any element that you have, the molar mass is going to be the atomic mass of that element. So if you've got sodium like we have here, this top number we should know is the atomic number. That tells us how many protons there are in a neutral atom. The decimal number that's underneath it is the atomic mass. So if you had one atom, it would have the mass of 22.99 atomic mass units. But if you have 1 mole of sodium, which is like saying 6.02 times 10 to the 23rd atoms, that has a molar mass of 22.99 grams. So all we did was express the atomic mass in grams. So these are just a couple of other examples of molar mass, just looking at one element. So if you have 1 mole of carbon, its mass is 12.01 grams. 1 mole of lithium, 6.941 grams. These are equalities. And whenever you see an equality, you can write a conversion factor. And we can use those conversion factors to convert from moles to mass and vice versa. Is everybody with me in terms of what molar mass is so far? Good. And we did this example last time too, but I want to go over it again. We talked about individual elements, but we need to talk about compounds. You can calculate the molar mass for a compound the same way you do for an element. You just have to add them up at the end. So we've got lithium carbonate, which is used to treat bipolar disorder. The three elements here are lithium, carbon, and oxygen. When you look at the periodic table, depending on which one you use, you'll see 6.941 for lithium, 12.01 for carbon, and then the one that I posted has like 15.999. I believe the one in your book has 16.0. They're so close you're not going to see a big difference in your answer. So for every mole of each of these, that's the number of grams associated with it. These subscripts we have to take into account. There are 2 lithiums in the compound. There's only 1 for carbon, and there's 3 for oxygen. You do all of your multiplication, and then you add it up. So why don't you give that a shot? Take a minute, put these numbers in your calculator, and add them up. Remember your sig figs here. There's 4 sig figs in the molar mass for lithium. So you need, yeah, you got 4. Never mind. I miscounted. So that's right there. So when you add all this together, that's what you should get. So 1 mole is equal to 73.89 grams. The other way that you can write this is to say 73.89 grams per mole. Are we good on that? Do you guys want to do an example on your own, or can we move on? Okay. So I have another one in here. I'll throw the answer in when I post the PDF of these notes. So just in case, you can go back and check yourself. I alluded to more calculations. That's pretty much the theme of this chapter. Molar mass, you can write as an equality, which means you can write conversion factors, and you can use those conversion factors to do math. We can go from moles to mass and mass to moles. So that's what we're going to do in this section. If we were to look at methane, methane has a molar mass of 16.05 grams. That's just the carbon plus the 4 hydrogens. The conversion factors you can write can have the grams on the top or the grams on the bottom, and you use the one that you need to get from point A to B. Let's do an example. I did this one in the video, but I'm going to do it again here, and then you can ask questions if you have them. Then I'll let you do an example on your own. We've got a box of table salt, and it has 737 grams of sodium chloride. How many moles are in the box? The first thing that I do when I'm doing these kinds of problems is identify the type of problem I have. The given information is a mass. The question is asking how many moles. Once I do that, then I know what conversion factor I'm going to need. The only thing that you can use to go from mass to moles is molar mass. And you're not going to have a nice little title that says converting mass to moles when you're taking your exam. So when you're doing these problems, even on your homework, when sometimes there's a title for the tutorial or whatever it is that you're doing, make this a part of doing the problem for you, because it will help you with taking the exam. I abbreviate molar mass mm. We're going to need the one for sodium chloride. So if you look at the periodic table, you find sodium, you find chlorine, you add them up. So you should get something in the ballpark of 58.443, depending on which periodic table you're using. You may have 3 digits after the decimal place, or 2. Your book typically gives 2, so just keep that in mind when you're doing your homework. We're starting with 737 grams of sodium chloride. We need to make a conversion factor to get from grams to moles. Where am I putting the grams? In the top or the bottom of the conversion factor? We're putting those grams in the bottom. That leaves the 1 mole to go in the top. When you do the math, you're going to divide 737 by the number of grams in 1 mole of sodium chloride. So don't forget, when you have a number in the denominator, the bottom, you divide. It's always a good idea to check your units. So the grams cancel and you're left with moles. Especially as these calculations get a little bit more complicated, you want to make sure that you're canceling out the right unit and that it's the right compound. Any questions on this? Then I want you to try one. You've got a sample of water. You've got the mass of the water. Calculate how many moles you have in the sample. I'll give you 2 minutes and then I'll check back in. I'll start writing it up here. We're trying to figure out how many moles of water we have in our sample. Whenever you're going from mass to moles, you need a molar mass. The molar mass of water is about 18. So if you had like 18.02 or 18, you'd be in the right ballpark. Starting with our sample, which is 59.8 grams, we need to write a conversion factor, and it's exactly like the problem we did before. We're going from grams to moles, so the grams in our molar mass go in the bottom of the conversion factor, leaving the 1 mole of water for the top. The grams cancel. You're left with moles. That's good. That's what we want. So you should get 3.32 moles of water. Questions so far? Or are we good? See a couple of you put your answer in and you got it, so hopefully that's more of you. As we get deeper into the chapter, it's going to be more imperative that you let me know if you're good. Because we're building. Each time we go through a section, we're building something else that we're going to pull from as we go forward. So far, what we have from last week and this week, we've got the definition of the mole in terms of the number of particles, using Avogadro's number. And then we added on molar mass. Now we're going to talk about those chemical equations we started off with in the first section of this chapter. We're going to learn how to write mole-mole factors from balanced equations and convert from the number of moles of one substance to another in a reaction. Inadvertently, when we were talking about balancing equations and making sure there was the same number of atoms of each element on the reactant side and the product side, we were talking about the law of conservation of mass. If you have the same number of atoms on each side, then the mass of those atoms is the same on each side too. What that means is that we're not creating or destroying anything. The same matter that existed as reactants is just rearranged to form the products. No change in the total mass occurs either. So the mass of the products is equal to the mass of the reactants. All of that makes sense if you think about what balancing a chemical equation really means. We can use that to talk about the relationships between the substances in an equation. If we were to make iron 3 sulfide from solid iron and solid sulfur, we can balance that equation. We have our coefficients. And remember that if there's no coefficient, you assume that it's 1. You can actually read that equation as 2 moles of iron combining with 3 moles of sulfur to give 1 mole of iron 3 sulfide. So instead of just having naked numbers, we can add moles behind it. And that will help us. With a mole-mole factor, I may also call it a mole-mole ratio. That's what some textbooks also call it. It's the same thing. It's just the ratio of the moles for any 2 substances in an equation. So let me show you what that means. Let's say I want to write a mole-mole factor that describes the ratio of iron to sulfur. There are 2 moles of iron for every 3 moles of sulfur. And that's a mole-mole factor. You can also write the reciprocal. So that's all you're doing, looking at the chemical equation and then writing out the relationship as a ratio. They look suspiciously like conversion factors because it's pretty much the same thing, only you're converting one substance to another. What if I wanted to write the 2 conversion factors, mole-mole factors, between sulfur and the iron 3 sulfide? What would I write? Don't all jump at me at once. Thank you. So we could write 3 moles of sulfur for 1 mole of iron 3 sulfide. And then we can flip that over. Does everybody understand that? Okay. If you have a specific question for me, that would be helpful. The 3 comes from the number that's in front of the sulfur. So whenever you're writing a mole-mole ratio, you're not making up any numbers. You're just taking the coefficient that's in front of each compound and writing that out as moles in a fraction. So there's a 3 in front of the sulfur, so we write that as 3 moles of sulfur. There's no coefficient in front of the iron 3 sulfide, but we read that as a 1. So 3 moles of sulfur, 1 mole of iron 3 sulfide. So just for clarity's sake, let's also write the ratios for iron to the iron 3 sulfide. we're looking at the 2 and the 1. So we'll write 2 moles of iron and 1 mole of iron 3 sulfide. Then you flip it. So how are we now? Okay. So try this learning check. You're going to see this equation a lot. It's the chemical reaction for making ammonia. Choose the option that could be a mole-mole factor for hydrogen gas and nitrogen gas. You can put your answer in the chat. Alrighty. So looking at the equation, we've got 3 moles of hydrogen gas and 1 mole of nitrogen gas. So we need to see those 2 things in the mole-mole factor. In A, there's 3 moles of nitrogen gas. That's wrong. B, we've got 1 mole of nitrogen gas, 3 moles of hydrogen gas. That looks like a winner. Let's check C. 1 mole of nitrogen gas, that's right, but it says only 2 moles of hydrogen. So it's gotta be B. Questions on that? It's definitely a problem type that you'll see on the exam. Let me know if we're good. Go for it, Jordan. So the numbers that you see for the mole ratio have to come from the chemical equation. And when we look at the coefficients, we've got 3 in front of the hydrogen gas and an implied 1 in front of the nitrogen gas. So the correct answer is going to have a mole factor with 3 moles of hydrogen and 1 mole of nitrogen. The only one that fits that is B. You're welcome. Of course, anytime you see something that looks like a conversion factor, there's going to be math. So just be ready, okay? How many moles of iron 3 oxide can form from 6 moles of oxygen gas? We're going to use a mole-mole factor to go from moles of the iron compound from moles of oxygen. This is where writing out your plan is really helpful. We're starting out with moles of oxygen. We're trying to figure out moles of the iron 3 complex. When you're writing your plan, be specific. Don't just write moles to moles, because that's not clear enough. It doesn't tell you what you're really doing. Now that I see I've got moles of oxygen and I'm trying to get to moles of a different compound, I know that I need a mole-mole factor. that goes between the two. So we'll set up an equation, but before we try to make the mole-mole factor, let's just write the two of them that we can make. So if we're dealing with oxygen and the iron 3 compound, that means we're looking here and here. Just give me one mole-mole factor that you can write that relates these two compounds. Yeah, we've got 3 moles of oxygen over 2 moles of iron 3 oxide, and then we can flip it. Which one of these are we going to use in our equation if we're trying to go from moles of oxygen to moles of iron 3 oxide? A or B? We're going to use B. That way we cancel out the moles of oxygen and we're left with the moles of iron 3 oxide. Before I even write in an answer, does everybody understand how we put this equation together? All right. We go through and do our unit analysis, and we check to make sure that we're left with the right thing, and we are. So you multiply 6 times 2, that's 12, divided by 3, that's 4. So that's what your answer should be. I want you to try this learning check, just to make sure that you've got it. I'll give you 2 minutes, and you can put your answer in the chat. All right. So if you haven't gotten to your answer yet, you can still keep working. That's fine. This time, we're going from moles of oxygen gas to moles of iron. Trying to figure out how much iron we're going to need to completely react with 12 moles of oxygen gas. So I agree with all of you that put C. The key to these problems is understanding how to write that mole-mole ratio. So if you don't know how to write those, going forward, the rest of the material is going to be difficult. So it may seem like, oh, why are we harping on this? But the reason is, this is the crux for everything else. So please don't be shy about letting me know if it still doesn't make sense to you. If you don't want to do that in the class right now, that's fine. But make sure that you do it. Come to office hours, send me a private chat during class, say something after class, whatever it is. Because the rest of the chapter is going to be really, really difficult. With that said, we're going to move on because we do have quite a bit to cover to finish chapter 7. So I will move quickly as long as y'all are with me. If you're not, then we'll try to slow it down and bring as many people forward as possible. So this is where you might want to take a deep breath. If you had chemistry in high school, you may have done stoichiometry, but it may be a little bit dusty, or it may have been something that you struggled with. What we're going to do at the end of this section is we're going to be able to take the mass of one substance in a reaction and use that to calculate the mass in grams of another substance within that same reaction. So I'm not going to, do a whole bunch of fluff beforehand. I'm going to show you the same problem I did in the YouTube video and walk it through and give you the opportunity to ask questions and kind of do it along with me. The best way to practice these mass-to-mass problems is literally that, practice. Once you get the method down and you pay attention to detail, you'll be fine. I told you you're going to see this reaction a lot. It's used in a lot of textbooks, very well known and understood. So we're making ammonia from nitrogen gas and hydrogen gas. And we want to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen gas. When we write down what it is that we're looking for, we've got grams of N2, and we're trying to figure out grams of NH3. There is no way to directly go from one to the other. We've got to make a couple of leaps. We can't really do a whole lot with grams, but we can do a lot with moles. So if we convert the number of grams of nitrogen gas to moles of nitrogen gas, then we can start doing some real calculations. What do we have to use to go from grams of something to moles of something? It's what we first started off this class with. Not Avogadro's number. That's to go from moles to number of things. It's molar mass. So to go from mass to moles or moles to mass, you need molar mass. So we're going to need the molar mass of nitrogen gas. From there, we need to figure out a way to get to moles of ammonia. The reason why I was harping on those mole to mole ratios is because that's what we need here. So we'll need to write one of those from the given equation. The last piece is to take the moles of ammonia and convert to grams. we're going to need molar mass again, but this time it's the molar mass of ammonia. So if you're a colorful person, if the colors help you with your visuals, definitely the time to pull out the color pencils or the markers or the highlighters, the crayons, whatever it is you use, watercolors, painting, get it done. The colors will help you see the different pieces when we arrange them. I'm not going to go through the trouble of writing out how to get the molar mass of nitrogen gas and ammonia. But if that's something that you still don't understand, that's okay. Just let me know in a private chat or something, or just let me know now and I can write it out. But until then, I'm just going to write out what the masses are. So those are the two molar masses we're going to be working with. Now let's build this equation. We're starting with the 32 grams of nitrogen gas. That's what we were given. The first conversion factor is going to take us from grams to moles of nitrogen gas. So if we were to stop there, we'd just have moles. We're not going to stop there. Now we need that mole-mole factor. What mole to mole factor am I going to write here to go from moles of nitrogen gas to moles of ammonia? Close. We need to flip that over. You want the 2 moles of ammonia in the top and the 1 mole of nitrogen gas in the bottom, because we're trying to cancel out the nitrogen gas and be left with moles of NH3. So what I did when writing out the plan was tell you what units you need at each step. So that will help guide you with where you're putting which piece of the conversion factor. Now we're going to convert the moles of NH3 to grams. We're going to use the molar mass for that. This time, the grams are going to go in the top, and moles will go in the bottom. Before you do any math and touch your calculator, make sure that you do the unit analysis and talk through your plan to make sure that you're doing the right conversions. The first step was getting rid of the grams of nitrogen gas and getting to moles. We used the molar mass of nitrogen gas, and that's what we did. The next conversion factor was a mole-to-mole factor, where we're taking the number of moles of nitrogen gas and converting to moles of ammonia. We wrote that mole-mole factor from the chemical equation. Now we're in moles of ammonia. Good. One more step. Convert the moles to mass using the molar mass of ammonia. We cancel out the moles. We're left with grams. So now we know what we get should be in the right units. When you're going through here, make sure that you multiply and divide as needed. So don't forget when there's a number that's different from 1 in the denominator, make sure you divide. Put this into your calculator and let me know what you get for the number of grams of ammonia. You should get 39 grams. So talk to me. Are we ready to try one? Do we need to talk through this one again? Let me know what you need. All right. So this is just the kind of the overall view of what we just did. I prefer giving you a problem to put context to it. But if you want a generic how to go from grams of A to grams of B, there you go. Here's the learning check. I will give you 5 minutes to do this. If I see you guys putting answers in the chat a little bit earlier, then I'll start setting up the problem. But I'm going to give you 5 minutes. If you don't finish in 5 minutes, that's okay. I want you to take your time, and if you get stuck, let me know. Then I can help you out. So take 5 minutes and try this problem. I'm going to get started with just setting up the equation, so keep working. We know the number of grams of iron 3 oxide, and we're trying to figure out how many grams of oxygen we need to make it. We're going to use the same exact method. And I'll try to keep the colors consistent as well. Let me know if you get stuck too, that's okay. Let me know where you get stuck so we can figure out how to get you unstuck. So there's our plan. Now I'm going to write out the equation. Yes, I can absolutely speak with you after class. No problem. I'm intentionally going a little slow here so that if you got stuck somewhere, you might be able to pick back up and finish the problem. So this is how it should be set up, where you're going from grams of iron 3 oxide to moles, then moles of iron 3 oxide to moles of oxygen gas using the mole-mole ratio, and then moles of oxygen to grams of oxygen using the molar mass. When you do all of that math, you should get B. So I know there are a couple of you that put your answer in. Everybody else, talk to me. Did you need more time? Did you get stuck? So remember, for this first conversion factor, what we're talking about is the molar mass. And that comes from this equality. So does that answer your question about the 1 mole versus the 2 moles? This second this second bridge comes from the mole-mole factor, and that's from the chemical equation. Yes, this video will absolutely be posted on Blackboard. I'm going to try to get it up between this class and my next class. Might not happen, but I'll definitely get it posted because I know it's an important one. Other questions? Because I know sometimes it takes a little bit to simmer. So you may not be able to jump in and just start doing the problems. You may not know why you're stuck. And that's okay. But if you do have questions, this is the time. If you're ready to move on, you can let me know. If you have a question, we've still got time for that. All right, then we'll keep going. We're going to build on top of those mass to mass problems by adding on two concepts, limiting reactants and percent yield. We'll talk about limiting reactants first. The limiting reactant is the one that's used up first in a reaction. And that's the reactant that limits the amount of product that you can form. So I gave a couple of examples in the YouTube video. I'll use a different example today. I'm probably going to have a grilled cheese sandwich for lunch. So that's where my brain is. For a grilled cheese, you need a couple of slices of bread. And if you're just going basic, like I'm probably going to go today, you're going to use 2 slices of cheese. Now, if I'm getting fancy, I'll use different types of cheese and all that jazz. But I ain't got time for that. You put them together, you get 1 sandwich. If I have 10 slices of bread, and I've got 4 slices of cheese, how many sandwiches can I actually make? I can only make 2. Because the limiting reactant, the cheese, I've only got enough for 2 sandwiches. The excess reactant is the one that doesn't get used up all the way. So in this example, the bread would be in excess. So it's a silly way to think about it, but it's honestly one of the best ways to get the concept of a limiting reactant and excess reactant. So are we good on that concept? Then let's bring it back to chemistry. I know it's lunchtime, but we're going to get to a break soon. Let's say that I have 3 moles of carbon monoxide and 5 moles of hydrogen gas. Those are my initial reactants. And I'm trying to figure out how much methanol I can make. I've got 2 different amounts. I need to figure out how much of the methanol I can make and which reactant is going to limit the amount of product. So what you're essentially doing is 2 problems. I know, that's what you want to hear, right? You have to do twice the work to answer the question. But it's not that bad, I promise. The first question that you have to answer is if you start with however many moles of carbon monoxide, how much methanol will you make? The second question is if you had all of that hydrogen gas, how much methanol would you make? For this first one, we're starting with 3 moles of carbon monoxide. We need a mole-mole ratio that's going to take us from moles of carbon monoxide to moles of methanol. Remember that there's a 1 in front of these compounds that don't have a coefficient. So our mole-mole ratio here will be 1 mole of methanol for every 1 mole of carbon monoxide. So that means we make 3 moles of methanol. Give the second one a try. Figure out how much methanol you would make if you had 5 moles of hydrogen gas. And you can put your answer in the chat. After about a minute, I'll start writing out the equation. So I agree with y'all. You're going to make 2.5 moles of methanol if you could use up all of that hydrogen. Now we've got to go back to the question. How many moles of methanol can be produced, and what is the limiting reactant? If we're mixing 3 moles of carbon monoxide and 5 moles of hydrogen gas, how much methanol are we going to make? Is it the 3 moles or the 2.5? It's the 2.5. You go with the one that makes the least amount of product. So we're going to make 2.50 moles of methanol. Which reactant is the limiting reactant? The carbon monoxide or the hydrogen gas? We said that we're going to make 2.5 moles of methanol, and that came from the 5 moles of hydrogen gas. So the hydrogen gas is a limiting reactant. So talk to me about that. How do we feel about it? Good. And again, for those of you who aren't chiming in, I get it. You might need to let it marinate a little bit. That's totally fine. But when you do have questions, please let me know. Get a tutor. Ask one of your classmates. Just don't sit alone and have question marks. I want you to try this problem. It's the same reaction. I've just changed the numbers around. And I want you to tell me how many moles of methanol you make and which reactant is the limiting reactant. I'll give you 3 minutes, but if I see people chiming in earlier, I'll start setting up the problem a little bit earlier. I'm going to go ahead and start setting up the problem. So we're literally doing the same exact problem, only we're swapping out the number of moles of each reactant. So when you do both of those calculations with 5 moles of carbon monoxide and 12 moles of hydrogen gas, you get 5 moles of methanol from the carbon monoxide and 6 moles from the hydrogen gas. For the amount of product you make, you choose the one that makes the least, which means we're going to make 5 moles. The reactant that was used to make that 5 moles of methanol is the limiting reactant. So several of you got that. Good job. If you didn't get it, that's okay. But make sure that you can get it because you've got your homework due this Sunday and you have an exam coming up. So don't get behind. This is a good place for a break. Yeah, so it's just a matter of how you write it. It's the chemist in me. I can't write methanol any other way other than CH3OH. That OH is an alcohol. That's a functional group. You'll learn about that in 105 if you take 105. So I can't, every bone in my body must write it CH3OH. I apologize. If there are no further questions, then we can take a break. We'll take a break until 12:30. We're doing pretty good on time. When we come back, we'll finish up with limiting reactants and then do percent yields. No problem. So, take a break, and at 12:30, we'll get started again. Alrighty, everybody, it's 12:30. We're going to get back to it so we can finish up. So as I promised, we're going to finish up limiting reactants. And we're going to do so by doing another problem. So this problem is a little bit more complex. And we are putting together the concept of doing the mass to mass problems along with the limiting reagent or reactant. I went over this example in the YouTube video, but I'm going to go over it here too. We have this reaction, and the question is asking how many grams of carbon monoxide are formed from 70 grams of silicon dioxide and 50 grams of carbon. We've got to do two problems here. The first one, we're taking those grams of silicon dioxide and converting to some number of grams of carbon monoxide. So let's start there. This is a mass to mass problem. Just like we were doing before, we're going to take the grams of silicon dioxide and convert to moles using the molar mass. The next step is to use a mole-mole factor to go from moles of silicon dioxide to carbon dioxide. The final step is using the molar mass of carbon monoxide to convert the moles to grams. I know I've said this a million times before, but this chapter builds on itself. So if you do not understand the mass-to-mass problems, then you can't do the more complex limiting reactant problems. All right. So that's the first part. We get moles of SiO2. Those cancel. We get moles of carbon monoxide. And then finally we cancel that and get grams. That's the first part. Are there any questions so far? We've only computed how much we would make if we had 70 grams of silicon dioxide. I'm going to push ahead and do the second part. And if you have questions, you can just jump on in. We're going to do the same thing, only we're starting with the grams of carbon. I'm not going to write the plan out this time, but I'll write everything in the same color scheme. So that's how you would set it up to go from grams of carbon to grams of carbon monoxide. So given these two values, how many grams of carbon monoxide are we actually going to make if we were to combine 70 grams of silicon dioxide and 50 grams of carbon? You're not going to add them together. We're either going to make 65.3 grams or 77.7. You're going to choose the one with the least product form. So think back to the sandwich example. So we're going to make 65.3 grams of carbon monoxide. That would make the silicon dioxide limiting. Are there any questions on that? I have a problem for you to try. So let me know if you are ready to just try the problem on your own. So here's your problem. We're back to making ammonia, and you've got 2.5 grams of nitrogen gas and 2 grams of hydrogen gas. Figure out how much ammonia you will make, and you can tell me which one is limiting if you want to. But the question is just asking, how much ammonia will you make? I'll give you 5 minutes, but if I start seeing answers coming in before then, I'll start setting up a little bit earlier. Again, for those of you who are not participating, you're kind of sitting in the background, that's fine. But make sure that it all kind of permeates your brain. And if it doesn't and you have questions, speak up through any of the ways that you can get to me. Course messages, chat during class, right after class, office hours. Okay, 5 minutes. I'm going to start setting up the problem, but keep on working. that's the first part. If we had 2.5 grams of nitrogen gas and we were reacting all of it, we'd make 3.04 grams of ammonia. We have to do the same exact thing, only with the grams of hydrogen gas. So if you were to use up all of that hydrogen gas, you would make 11.3 grams of ammonia. We can't make both. We can only make one. So you choose the one that you make the least product, and that's 3.04 grams of ammonia. So that's as complex as it's going to get for limiting reactant problems, where you have to do 2 mass-to-mass problems and then figure out which one is the limiting reactant and how much of the product you're going to make. So these problems can take a little while. If there are any questions, let me know now. If you need to go through it again, or if it just needs to simmer, you can let me know that too. Let me know. It needs to simmer, Dr. H. Just keep going and let it simmer. So generally speaking, when you see, however you see the initial reactants given, that's how the product should be given too. So we're given grams, so you need to give grams of ammonia. An amount of ammonia also implies the mass. No problem. And let me know if you're ready to move on, because we've still got more to cover. So the second part of this, we talked about limiting reactants. Now we're going to talk about actual theoretical and percent yield. In the real world, there's still conservation of mass, but the amount of product you get likely will not equal the same amount of the reactants that you put in. Some processes you lose some, you drop some, doesn't go to completion. So all kinds of things happen. The theoretical yield is the maximum amount of product that you can make. And that's what we've been calculating. So all these problems where we're doing the mass to mass and stuff like that, or moles to moles, that's the theoretical yield. The actual yield is what you obtain experimentally. And you'll always be told what that is in the problem. The percent yield is the ratio of what you actually make to the theoretical yield, or what you calculated you'd make. And then you multiply that by 100%. So I'm going to go through a problem for you that is as complex as it's going to get for an actual, for a percent yield question. The first part of it is going to be a mass to mass problem. And then the second part is going to be the percent yield. I'll show you the mass to mass. And then I want you to do the percent yield once we get the theoretical yield down. I know that seeing the mass to mass problems done over and over and over again can be really helpful. So if you got it already, good. If you don't, I got you. So on a space shuttle, you've got lithium hydroxide, and that absorbs the carbon dioxide that you're breathing out, and it forms lithium bicarbonate. What is the percent yield of the reaction if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? You have to recognize what is given as a reactant mass and what's given as the actual yield. The 50 grams of lithium hydroxide, we see that that's a reactant. So that must be the mass of our starting material. The 72.8 grams, that's our product. We can label that as the actual yield. We'll need that when we're calculating the percent yield later. Since it's a mass to mass problem, we're going from the grams of lithium hydroxide to the number of grams of lithium bicarbonate. And this is the theoretical yield. So I'll write that out for you. If you want to try to do it alongside, you can. As always, the first step is converting to moles. Then we write a mole-mole ratio. And here, it's 1:1. The last part is converting the moles of product to grams of product. And when you do that math, you should get 142 grams of lithium bicarbonate. But that's not the end. That's just our theoretical yield, the maximum amount of product that we could make. The percent yield is the actual over theoretical multiplied by 100%. So why don't you go ahead and calculate the percent yield and put it in the chat. To set this up, yep, I was just trying to wait for a few more answers, see how people are doing. You're going to take the actual yield, which is from the problem, that's 72.8 grams, and divide by what we just calculated, which was the theoretical yield, 142 grams. So it should be 51.3%. Make sure that when you're putting in the actual and theoretical that you don't switch them. So this is the only new part for percent yield. Are we good on that? All right. This is the last section. A little bit easier. We've been doing a lot with these chemical equations, doing a lot of calculations, and predicting how much of a product we'll make, what's the limiting reactant, all that stuff. Something else that we need to take into consideration with chemical reactions is the amount of energy that's gained or lost. The amount of energy that it takes for a reaction to go is the heat of reaction. So you're either going to absorb heat or release heat during a reaction. And there's several places during the course of a chemical reaction where energy changes. So let's say that we've been doing a lot with this ammonia equation. During the course of this reaction to make ammonia, the hydrogen gas and the nitrogen gas have to find each other and interact. Once they interact, then the bonds between the hydrogen gas, so the hydrogen atoms, and the nitrogen atoms have to break apart. That's a change in energy. When those atoms recombine to form ammonia, that's going to be another change in energy. So the total of all of those processes is the heat of the reaction, and the symbol is delta H. You can calculate delta H simply by taking the heat of the products and subtracting the heat of the reactants. We're going to add on to our terminology here. For an exothermic reaction, you're going to release heat. So when you start off with your reactants, they're going to be higher in energy than your products. When you release heat, you can think of heat as a product and write it in on the product side. When you see a delta H, exothermic reactions will have a negative delta H. Endothermic reactions are the opposite. Means that heat is absorbed. So if you're doing something in a reaction vessel, that vessel is going to get cooler because the reaction is absorbing heat from the environment. The reactants require energy, so the product is going to be at a higher energy than the reactants. And if you want to add that heat to the reaction and write it in, it's going to be on the reactant side because you need that added heat to make the reaction start. The delta H for an endothermic reaction is positive. So you need to know those terms. You need to understand the difference in energy between the products and the reactants, and what that means for the sign of delta H, whether it's positive or negative. Is that clear so far? We'll keep talking about it, and I think it'll become a little bit more clear. When we're talking about the delta H, the heat of the reaction, we can treat it just like one of the substances in the reaction, because for a certain amount of moles of X, you're going to absorb or release a certain amount of heat. So if we're taking water and we are decomposing it to make hydrogen gas and oxygen gas, the delta H is going to be positive. That means it is endothermic. Requires heat in order for this reaction to happen. If you require heat, then you can think of it as a reactant. So you put it on the reactant side. And just like you could write a mole factor for how many moles of hydrogen gas you would make for however many moles of water, you can write how many joules of energy you need for each of those values too. So if you have 2 moles of water, you need 572 kilojoules of energy. So it's the same thing for all of those. And I think it'll become even more clear when we do a problem. So I'll do a sample problem for you, and then you can ask questions. Then I have a problem for you to try. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? We've got 50 grams of ammonia, and we see that our delta H is negative. So is this process endothermic or exothermic? It's exothermic because we are releasing heat. It's got a negative delta H. So if I were to rewrite this chemical equation, I would include the heat on the product side because it's endothermic. So that's just a kind of a review of what we just went over. Now, we've got 50 grams of ammonia. We can't do anything with grams. We always need to convert to moles so that we can use conversion factors to get from point A to point B. So that's where we start. We've got moles of ammonia. Now we need to figure out the energy associated with that number of moles. And we're going to write a conversion factor just like we would with anything else. We want the energy and we want to cancel out the moles. So we're going to put 2 moles of NH3 on the bottom and 92.2 kilojoules on the top. That's how we made our conversion factor. We figured out what we need to cancel, and then we looked at the chemical equation and wrote down exactly what we saw. Now we can get rid of those moles and multiply and divide our way through. When you do that, that's what you should get. Questions? If you're good, I have a problem for you to try. Then try this one. You've got 50 grams of hydrogen gas reacting with excess nitrogen gas. How much heat is released? I'll give you a few minutes and then check back in. Here we go. We're starting with 2 grams of hydrogen gas. As always, you've got to use that molar mass to get to moles. Then you write a conversion factor that tells you about where the heat is. Oh, whoops. My bad, y'all. We need to do the mole to mole thing, right? We can show that to show how many moles of ammonia you get. We don't have to go into all of that. We care about the heat. Same exact thing as before. Only this time, we've got hydrogen gas that we're concerned about. So how much heat for every 3 moles of hydrogen gas? We've got 92.2 kilojoules. We can go through and do all the math. Oh, I wrote 2 instead of 50 because my brain is on lunch. That's why. Thank you for that. The calculation I did is for 50. Good thing I did this earlier. Thank you. So, with 50 grams, we've got a lot more moles of hydrogen gas. And you should get something in the ballpark of 762 kilojoules released. So that's it for chapter 7. Are there any questions on this? As always, I've got your reminders here. So chapter 7 assignments are due on Sunday by 11:59 p.m. If you have questions, you can always send them to me using course messages. Just remember that I don't always get back to you that instant, but I check them pretty regularly, especially during office hours, which are Wednesdays from 2 to 4 p.m. If you need time outside of that, you need to let me know early. So if you know, okay, this is going to be a struggle, send me a message, because if I don't see a message before the end of the day, like end of business, then I may not be able to accommodate you at an earlier time tomorrow. Your exam 3 is going to cover chapter 7 and 8. Chapter 8 is gases, so it's gas laws and doing calculations with those. I've already posted the video and the notes on YouTube, and you'll see a chapter 8 folder already posted in Blackboard. So make sure that you get a chance to go over that video before we have class next week. It's not as bad as this chapter, in my opinion. Just takes a little bit of practice. That's all that I have for you. If you don't have any questions, you're free to go. Go for it. Yes, it's already made and posted. You're welcome. Yeah, that's fine, Alicia. We can talk. If you want to wait until folks are gone, that's cool. Everyone's signing out now. So it looks like there's one more person. Kendall, are you still here? No problem. Okay. How can I help? Oh, hold on. 1 second. Let me